Thank you all for joining us for the inaugural Texas FIRST Robotics Competition workshop, hosted by FIRST RGV. A little bit about us, and then we will turn it over to our presenters today. FIRST RGV is a nonprofit founded in 2015 that supports the FIRST community in the Rio Grande Valley, which is an area approximately 3 hours long by 2 hours wide, sits next to the border of Mexico. Yes, in Texas, it's easier to measure by driving hours than miles, just because Texas is just large. Since 2015, we have seen explosive growth of teams in our FIRST LEGO League and FIRST Tech Challenge program, but our growth in the FIRST Robotics Competition program is positive, but we are not where we need to be on ensuring access to the more than 250,000 students in the K through 12 space here in the Valley. With our events like this, we are doing our part to create awareness of our efforts and the need for strong sponsors and mentors to help our community. We are proud Texans, and I'm honored to be part of the FIRST in Texas Robotics Territory. Our organization is proud to be hosting this weekend's event. If we have any technical issues, please remain patient. We will get them resolved as quickly as possible. While you're engaging in the chat, asking questions, and saying hi to your neighboring team, or maybe a team across Texas, we ask that you remain on topic and know that this session is being recorded for teams to take advantage of this great information later. We will post this information on the FIRST RGV YouTube channel, and you can access it directly by visiting youtube.firstrgv.org or by searching for FIRST RGV on YouTube. I want to personally thank the FIRST Robotics Competition teams across Texas that have come together this weekend to make this live event possible, and for the hard work of our FIRST senior mentors and AmeriCorps Vistas across Texas that stand ready to help support our teams. On behalf of FIRST RGV, we hope everyone has remained safe during this pandemic, and we are confident that all of the partners across Texas will be getting ready to bring you a robotics season soon. Thank you.
Hi, my name is Unity Perry.
And my name is Catherine too.
And we're going to be presenting LabVIEW basics. First things first, y'all need to download a bunch of different things so you can code in FRC Robot. We made a Google Doc with all the steps to get you set up. After going through the doc, y'all will have everything you need to program an FRC Robot. Skip any of the steps if you already have that part downloaded. The downloads must be done and they take a lot of time and require you to restart your computer, so do them after the presentation. Once you open up LabVIEW, you should see this menu pop up. Select the RoboRIO project if you want to run code for your robot. It provides a simple template that you can adjust based on what you want your robot to do. The other type of project you see is the dashboard project. That type of project is used for making custom dashboards.
After clicking on the RoboRIO project, you should reach this screen. Fill out the project name and the team number inputs. Make sure to name your projects properly, since it's easy to tell which project is for what, and because you can't have two projects with the same name. Then, there are 4 options for you to select from. The bottom 2 are simulations, which are good for visuals. The other 2 are what you use for coding a robot, arcade drive and command and control. For now, we're going to deal with arcade drive. At the top of the project structure, you have the target. The target represents where the code would be run, in which this case is the RoboRIO. Everything below the target is run on the RoboRIO. Everything in the support code folder is a bunch of custom-made sub-VIs used throughout the robot code. The team code folder has all the template code for the robot. Those are the files where you will be putting your robot code. Everything in that folder is important and cannot be deleted. Another folder is called support code, and inside there's an elapsed time VI. When running the robot main, it's like a stopwatch. counting how many milliseconds has gone by since pressing run. And also, notice under target, there's a team code folder, which has a bunch of subsystems within it. Also notice how robot main is not within that folder, which we'll talk about later.
Robot main is the full picture of your code. This is the VI that you run on the robot. Everything else happens inside of it. This is built-in code, so we don't directly do anything in this VI. We modify and add to the sub-VIs inside it. On the left, you can see notes that describe what's going on inside the VI. Every subsystem has notes on what it does in detail, so you can read them if you're confused. Like the name says, this is the beginning of your code. This is the first subsystem that is run, and it only happens once. Since it only runs once, we do things like initialize motors, sensors, and controllers because they don't need to be repeated. How we do those is by opening the various components and telling them where they're being plugged in. We then give each of them a name. This is because we need to use these again in another VI, and we identify them through a name. As you can see in the picture, we are opening our joystick, motor, and limit switch. Then we set its ref num as a string, which is a name we give to it so it can be accessed and identified later in the code.
Teleop is the other key VI in the arcade drive. And just like the other VI, it indicates what it does. The teleop VI is run when the teleop portion of the game is being played. This VI is run in a loop the whole time teleop is being played. Teleop VI primarily focuses on using input from the Xbox controllers the drivers are using to determine what speed the motor should go to. Like we mentioned, we use the names to identify each different component, and then based on driver controls, we change the speed for motors or use sensor data. In the code, we are taking joystick values and indexing them to get a proper X and Y value. Then we put those values into the motor set output. Switching gears a little bit, we're going to go to command and control, which is the other type of project for coding a robot. If you notice, in Arcade Drive, everything happens in two VIs, begin and teleop. Command and control takes a completely different approach. It's based on the assumption that the robot can be split into relatively independent subsystems. For example, a drive base is coded completely different from a shooter.
Since this approach breaks every robot into multiple subsystems, the template code provided is more generic. Every robot is different, and everyone breaks their robot into subsystems differently, so that's left to the people coding. If you choose to make a subsystem, right-click on the target and go to New, and then go to Subsystem. This creates a new subsystem, which you can name accordingly. There is a bug with doing this with LabVIEW when you download it, but there is a fix which we have a link to at the end of our presentation. The command and control project structure is way different than Arcade Drive, but one commonality is everything falls under target because the code is still run on the RoboRIO. As shown in the last slide, when you make a subsystem, a folder is created. Here, we create a drive-based subsystem, and within the folder, you have two subfolders, which are commands and implementation. There's also a couple of new VIs, such as periodic tasks, subsystems, and vision processing, which we'll talk about later.
Robot main is pretty similar to the version in Arcade Drive. It's still the VI you run for your robot code, but one thing to note is that there's a subsystems VI on the bottom. We'll be going more in depth on this VI, but since this new project structure is based on subsystems, there's a subsystem VI. In the code, the begin VI runs first, which opens all your Xbox controllers. Then the autonomous runs next, which executes your 15-second program. Lastly, the teleop VI runs, which is the driver-controlled period of the game. A common trend you might be noticing is that these VIs are relatively unchanged in when they're run or how they are run. When we change is what happens inside the VI. And for begin, the major change is that we no longer create motors or sensors. Since we are under the assumption that each subsystem is independent, then we assume the motors are independent as well. Begin is much more general, so we do one-time things that apply to the whole robot. For us, we only open Xbox controllers.
This is probably the most important VI in command and control. This is the VI in each subsystem folder where all the code is. This VI is run once. Everything to the left of the loop happens once, which is why we open our motors there. The reason we don't give them a name is because that is only needed when you do it in two different VIs like begin and teleop in the arcade drive project. But since all the code is in one VI, it doesn't need a name. Then we put all the code for setting powers inside the while loop because that happens repeatedly, like teleop. In the program, you can see that we open the motor first and set its CAN ID, which is unique to each motor. Then we set the output of the motor inside the loop. We take the controller values passed along in the teleop VI and set it as the motor value, which we will talk about next. Since the code for controlling motors is in a different VI, we can't do that in this VI anymore, like we did in arcade drive. But teleop is still the main VI being run during the teleop part of the game. How that works is you get an Xbox controller values and send them to each individual controller VI. To do this, we have a middleman VI called drive base immediate. For each different subsystem, for every different subsystem, there is an immediate VI under the commands folder. In the code, we take the joystick's values and index them based on what buttons you want to use. We pass those values into the controller VI using the drive immediate block.
This is the VI which runs each subsystem's controller VI. This is a very useful VI for debugging, because if you have a problem and you only want to run the drive-based VI, all you need to do is disable all the other subsystems. This VI automatically updates as you create new subsystems, so you don't have to worry about it other than for the debugging purposes. The yellow block is the periodic tasks VI, which we'll talk about next. In the code, each of these green blocks you see are the controller VIs for each subsystem, which executes the code. The periodic tasks VI focus on tasks that happen at the same amount of time. You can create as many loops and change the wait time, so each loop runs at a different rate. Most of this is used for publishing values to network tables for dashboard projects.
So remember how we said command and control is based on the concept of mainly independent subsystems? Well, what if there's a dependency between them? For example, the shooter will only work if the intake has a ball. How can they communicate to each other to let each other know that there is a ball there? That's why there's a robot global data VI. It's just a front panel where you can put controls to represent variables. So in our example, you would have a Boolean global deciding whether you have the ball or not. And in the intake controller VI, it would write a value to that global, and in the shooter controller VI, it would read that value. Like the name says, this VI can be used for vision processing. If so, vision must be enabled in robot main. It works with most external cameras. You can take the feed and do anything you want with it using the NI Vision development module. A use for this case this past year could be the detecting the power cells.
Like in teleop, where you use the middleman to send values to the controller, the autonomous VI also does something pretty similar. It uses various VIs in the command section to send different commands. And instead of sending Xbox controller values, we pass in predetermined numbers. That eliminates the use of Xbox controllers, making it autonomous. When you group these commands together, that will be your autonomous program. Now we know how to code a robot, but we don't know the most important part, how to actually run it on the robot.
To do this, right-click on the target and hit Properties. Change the IP address to 172.22.11.2 and hit OK. These steps will allow you to connect to the robot through USB. To connect to the robot wirelessly, do the same steps as the previous slide, but change the IP address to 10. Then the first 2 digits of your team number, then the last 2 digits of your team number, and then .2.
Hit the arrow on Robot Main after you've connected to the robot. If you click the single arrow on the top left, the code will run once. In order to stop it, you press the stop button that we circled right next to it. When deploying code to the RoboRIO, you first want to open Build Specifications, then right-click and hit Build. Once it's finished building, hit Run as Startup. This will allow you to play the code on your robot. After deploying the code onto the robot from the dashboard, you can enable and disable the robot. The next few slides will show you the steps of coding this drive base. Let's get started.
In the Begin VI, we open the joysticks and give them a ref num so we can access them later in the teleop VI. Now in the Controller VI, you set the motors like we said before, and to do this, open the WPI palette, go to Third Party to get the blocks needed. First, we open our motor, and then we set the CAN ID values, which differentiates each motor. Then we set the output of the motor inside the case structure using an advanced set output block. When coding a drive base, it's important to remember to reverse one side, and we do that by setting the inverse Boolean to true. To give the motor actual number values, we hook up the left and right set points from the cluster into the motor value, which are coming from the arcade drive block in the teleop VI. The other subsystems are pretty similar, only needing to change how many motors and what type of motor. In this code, we index the joystick values based on what indices the X and Y values are. Then we take those joystick values and put them into the arcade drive sub-VI, which makes the drive base move properly. The arcade drive block outputs motor values, which are fed into the drive immediate VI. And this goes into the cluster and the teleop VI as the left and right set points like we said earlier. We also passed in joystick values from controller 1 to the shooter and intake controllers for their motor speeds.
Here's a fun fact for y'all that we couldn't pass up not saying on this presentation. On 2687 and 2468, we call the wires in LabVIEW spaghetti, since when there's more code and it gets messier, the wires look like spaghetti. And now that we're talking about chefs and spaghetti, we wanted to show you a menu of LabVIEW hacks that we cooked up for y'all. Like, if you wanted to fix broken wires, you'd press Ctrl B and all the wires that were broken would disappear. We have some resources for y'all that are interested. This is where you can find more information on the broken wire bug when creating a subsystem, like mentioned before. We have a lot of different resources that are useful. We'll post the slides right now into the chat for those who want it. If you have any problems with accessing the slides we put here in the chat, you can email this email and we'll manually add you. Thanks for listening. Happy coding.
if there is any questions, now's a great time to ask those in the YouTube chat for session number 1 for LabVIEW. So we'll give you a minute here to post any questions that you may have live on YouTube. All right, we don't see any questions coming in, so what we'll do is we will break and we will come back at 4 o'clock sharp for the start of the second half of this presentation, where we will deep dive a little bit more into LabVIEW. So if you think of any questions, hang on to them, and you're welcome to ask them in the second session. But for now, we will close out this session, and we'll see you back again at 4 o'clock. Thank you. This concludes this session. If you're watching us live, please take the time to go back to YouTube and pick up our next session, or you can always visit our live page at firstrgv.me/live and pick up the next session there. We appreciate you watching and participating in today's session.